we had been discussing the significance of Boyle temperature, in the previous video we mentioned one significance of Boyle temperature, and in this class we will mention the others. The ideal gas behavior corresponds to the compressibility factor being equal to 1 at all temperature and pressure, that is a plot of Z versus P, or 1 by V or 1 by Vm, Vm being the molar volume, will give a straight line at Z is equal to 1 at all temperature and pressure. This characteristic of an ideal gas is based upon certain assumptions, namely that the constituent molecules of the ideal gas have zero size, that is they are point particles, and the constituent molecules of the ideal gas do not interact, that is they neither attract nor repel, and so have zero potential energy. The same plot, the Z versus P plot, was obtained for gases that exist in reality, namely oxygen, nitrogen, hydrogen, carbon dioxide, and so on and so forth. That is for real gases, and a different pattern was visible, namely this is the abscissa along which we plot P or 1 by V or 1 by Vm, and in the ordinate the compressibility factor Z, and this is Z is equal to 1. At Boyle temperature, the compressibility factor for the real gases vary as follows. So this is how they vary at T equal to Tb, the Boyle temperature. Clearly, up to certain range of pressure, the compressibility factor is 1, and at higher pressures, Z is greater than 1 as the curve turns over and moves up. At temperature higher than Boyle temperature, that is at T greater than Tb, this is the plot that is obtained, and it corresponds to Z greater than 1. And for T less than Tb, the curve is of the following type. And it has a portion corresponding to Z less than 1, but the curve turns over and moves up, and at high pressure Z is again greater than 1. The Boyle temperature thus has the significance that at this temperature real gases behave in an ideal fashion up to some range of pressure decided by the nature of the gas. So this was the first significance of Boyle temperature. So temperature at which real gases show ideal behavior over a certain range of pressure. This is the first significance. Let us note that for ideal gas, Z is equal to 1, which means the ratio PV by nRT, where V is the ideal gas volume, is equal to 1. This is in fact written as Z ideal, and for real gas Z is not 1 in general, as evident from this plot. Only up to certain range of pressure at Boyle temperature Z is equal to 1 for a real gas. In all other cases, Z is either greater than 1 or less than 1. So, Z assumes the values under different situations. In view of this, we can write the compressibility factor as the ratio PV by nRT, which was the definition of Z, the compressibility factor, but now this V represents volume of the real gas, and this is Z real. Let us consider the ratio Z real to Z ideal. Now Z real is Z and Z ideal is 1. Again, Z real is this quantity, and instead of Z ideal we can write this quantity. So simplification gives us Z to be the ratio of V real to V ideal. So we have got this result, which we will be using over and over again. And let us note that V real represents the volume of real gas, and V ideal represents volume of the real gas had it been ideal. It is had it behaved in an ideal fashion, that is, behaved ideally. In view of this graph of Z versus P, and due to this relation, further discussion will be easy if we divide things into 3 cases. Depending upon the values of Z, namely Z greater than 1, at which V real is greater than V ideal, and then we can consider Z is equal to 1, which corresponds to V real equal to V ideal, and finally Z less than 1, for which V real is less than V ideal. Let us find from the plot when Z greater than 1 occurs. Z greater than 1 occurs for t greater than Tb, as well as for t equal to Tb, and also for t less than Tb. So it can occur for any t. Z equal to 1 occurs only for t equal to Tb up to this amount of pressure, that is in a specific or certain range of pressure decided by the nature of the gas, the real gas. Say 0 to P, and Z less than 1 occurs for T less than TB, as we can see here for low pressure region. We shall now discuss these three cases separately as follows. For Z greater than 1, we are here, that is above the Z is equal to 1 line. Obviously, in this region Z greater than 1, the real gas shows a positive deviation with respect to the ideal value. So, this corresponds to a positive deviation. And Z less than 1 means we are here, that is below Z is equal to 1 line, so real gas shows a negative deviation. Since things are measured with respect to ideal behavior, it follows that when real gas exhibits Z is equal to 1, it behaves ideally. That occurs at Boyle temperature over a certain pressure range, and so clearly Z is equal to 1 corresponds to zero deviation or no deviation. This is the reference point with respect to which deviations are calculated. So no deviation over a certain pressure range. For Z greater than 1, V real is greater than V ideal, which means the real gas expands. So this corresponds to expansion. On the other hand, for Z less than 1, V real is less than V ideal, which means the gas contracts or gets compressed. So this corresponds to compression or contraction. Clearly, expansion corresponds to Z greater than 1. Again, expansion means molecules move away from each other. That is, they repel. Molecules do not like to stay together. Or close enough. But scatters. Or spreads out. Clearly, in this situation, repulsive force dominates. And since repulsive force dominates, the gas will be difficult to compress. So the key points for Z greater than 1 situation is that it corresponds to expansion where molecules repel each other, the repulsive tendency dominates, repulsive force makes its presence felt, and because of this repulsive tendency of the molecules, the gas is difficult to compress, and that again means that the compressibility factor exceeds unity. For the case Z is less than 1, V real is less than V ideal, which means the real gas occupies less volume, that is, it contracts, and this is possible if molecules move towards each other. That is, they are attracted. They like to stay close. Or together. In other words, they equalize. Clearly now, attractive force dominates. And this means the gas is now easy to compress. So the key points for Z less than 1 situation is that the molecules exhibit attraction, that is, attractive force dominates, and hence the gas is easy to compress as indicated by a compressibility factor that is less than unity. From the discussion that we have just completed, it follows that Z greater than 1 means the gas expands and repulsive force dominates in this situation, while Z less than 1 corresponds to compression or contraction in which attractive force dominates. Let us now consider the situation corresponding to Z is equal to 1. Z is equal to 1 means there is no deviation. In other words, gas neither expands nor contracts with respect to the ideal volume. And this is possible only if the repulsive tendency and the attractive tendency balance each other. So, for Z is equal to 1, the attractive and the repulsive tendencies balance. We can write in short that attraction is equal to repulsion. The amounts are equal. The forces are equal. In other words, net molecular interaction is zero, as if molecules do not feel each other's presence. They are independent of each other. They are not influenced by one another. And this was exactly an assumption or basis of the ideal gas model. So we can state that Z is equal to 1 corresponds to an ideal behavior. of the gas. And this occurs at Tb, that is the Boyle temperature. So this is another significance of Boyle's temperature, at which attraction and repulsion cancel out because they balance each other, making net molecular interaction vanish. So this is the significance of Boyle temperature. We shall make a gist at the end of this lecture regarding significance of Boyle temperature. Let us now re-explain these things, but now in terms of van der Waals constants. The van der Waals equation of state that describes a real gas is given by where A and B are called the van der Waals constants. And the significance of these constants are that A has attractive influence while B has repulsive influence. And let us combine these facts. Since for Z greater than 1, repulsive force dominates, it follows that the van der Waals constant B dominates for Z greater than 1 situation, and for Z less than 1 case, attractive force dominates, which means in this situation van der Waals constant A dominates. So it is the influence of B that dictates everything in this region, while it is the influence of A that controls the behavior of the real gas in this region. And for Z equal to 1, the repulsive influence of van der Waals constant B is neutralized by the attractive influence of the van der Waals constant A, as a result of which there is neither net attraction nor net repulsion. So attraction equal to repulsion, molecules do not interact on the whole, and the real gas behaves ideally at Boyle temperature up to certain range of pressure. So this is another significance of the Boyle temperature Tb. We next move on to state the other significance that can be attached to the Boyle temperature Tb. This is the Z versus P plot, and let us show the plot for T equal to Tb separately. So this is the plot at Boyle temperature. In the abscissa we can plot P or 1 by V or 1 by Vm. And this straight line portion indicates that real gas behaves ideally up to this point, that is up to this amount of pressure. Since this is a straight line which is parallel to the pressure axis at z is equal to 1, it follows that the slope of this portion is 0. Let us write it clearly or properly. It follows from the plot let us take p tends to 0. So limit p tends to 0. The slope of z versus p plot, and the slope is del z del p, and the slope is for the plot obtained at T equal to Tb, the Boyle's temperature. And this, being parallel to the pressure axis, is 0. That is, slope of z versus p plot at low p is 0 at Boyle's temperature Tb. So this is the significance of the Boyle's temperature. Having written down this condition, let us focus attention to the Virial equation of state, according to which the compressibility factor Z, which is the ratio of PV and nRT, can be expressed in terms of a power series in pressure P. So this is a power series in P where A, B, C, D and so on are the virial coefficients. And A is the first virial coefficient, B is the second virial coefficient, C is the third virial coefficient, and so on. Let us put this value of Z in this condition to get in the next step we get this gives just B in the left hand side at T equal to Tb. To be equal to 0. So we arrive at another significance of Boyle temperature. It is that temperature at which the second virial coefficient B of the virial equation of state vanishes. So we can write it down that Tb, the Boyle temperature, is the temperature at which the second virial coefficient B is 0. We shall discuss this in more details, and we shall spell out the physical significance of the fact that virial coefficient B vanishes at Boyle temperature in the video on problem on Boyle temperature. Let us now summarize or make a gist of all the significance that can be attached to the Boyle temperature. Gist on significance of Boyle temperature. Boyle temperature, that we denote by TB, is the temperature at which real gas behaves ideally up to some range of pressure. Boyle temperature is the temperature at which attractive and repulsive interactions between constituent molecules balance each other, so that net interaction is 0. In other words, the real gas does not show up any internal interactions at this Boyle temperature. All internal interactions vanish. Boyle temperature is a temperature at which repulsive influence of van der Waals constant B is neutralized by the attractive influence of the van der Waals constant A. Boyle temperature is a temperature at which slope of Z versus P, Z being the compressibility factor, plot at low P, that is pressure, is 0. That is, Boyle temperature is that temperature at which the second virial coefficient of virial equation of state is 0. That is, the second virial coefficient is denoted by B, in the next video on Boyle temperature, we will derive expression of this Boyle temperature and then proceed to solve some problems on Boyle temperature.